So good afternoon, sir. Raju here. Narendranath, sir. You mute me. ಇದರಪ್ಪ ನರೇಂದ್ರನಾಥ್. ಲಾಗ್ ಔಟ್ ಅನ್ಸುತ್ತೆ ನೋಡಿ.
Good afternoon, everyone, and all the participants. The session will be starting in another 2 minutes. The speaker is going to join. All of you, please, in the meeting itself.
Good afternoon, sir. Am I audible, sir? Unmute yourself, sir. Unmute. Sir Narendranath, sir, you can unmute yourself.
Yes. Now?
Yes, sir, you're audible, sir. You're perfectly audible.
Please. So
Yes,
sorry for the inconvenience.
Yes, sir. Yes. No problem, sir. Sir, I would like to welcome to this afternoon session. From morning, people have been actively involved in this FDP, and so many questions were posed to the different experts. So, good afternoon, dear participants. Today we have with us Dr. Narendranath, who is working as a professor in Department of Mechanical Engineering in NIT Surat, right? Now, he has got varied interest in research which spans from shape memory alloys to machining parameters and other things. And now he has given his consent to deliver this expert lecture in this faculty development program. On this occasion, I thank him for wholeheartedly accepting our invitation to deliver the lecture. And I now request Professor Bairegoda to give a brief introduction about the speaker.
Thank you, Dr. Raju sir. And good afternoon, all the participants and session speaker, Dr. Narendranath sir, for the 9th session of FDP on rolling and characterization of SMEs. And Dr. Narendranath S is a professor in the Department of Mechanical Engineering, NIT Surathkal. And Dr. Narendranath has a total work experience of 27 years, which includes 23 years academic experience, 3 years research, and 1 year industrial experience. And his academic qualifications are PhD in the year of 2006 from IIT Kharagpur on smart materials, and MTech in 1993, University BDT College of Engineering, Kuvempu University on production engineering and system technology, and he got BE in 1989 from Government BDT College of Engineering, Mysore University, Davangere. And his areas of interest are conventional and advanced machining processes, casting and welding, materials and characterization, shape memory alloys, that is smart materials, corrosion, equal channel angular press. And is also having membership in this professional bodies, in that Indian Society for Technical Education, Metrology Society of India, the Institution of Engineers, the Indian Institute of Metals. And Dr. Narendranath is having some honors and awards, that is received Best Paper Award by ICDMC in the year 2019, and on the role of processing temperature in equal channel angular extrusion, microstructure, mechanical properties, and corrosion resistance. And also received participation certificate from Dr. K.V. Rao Research Awards 2019 in chemistry on a novel approach to improve the corrosion resistance of AZ80 Mg alloy through ECAP. And also he received Best Paper Award by ICONMAT in the year 2019 from Cochin University, and received Best Paper Award by CDAMIES 2018 from NIT Tiruchirappalli, and received Best Paper Award by CDAMIES 2018 from NIT Tiruchirappalli, and certified that review on non-conventional machining of shape memory alloys transactions, and Best Poster Award by ICA MDD from Goa, December 14 to 16, 2005. And Dr. Narendranath has published his work in N number of national and international reputed journals, and also presented his work at different level of conferences. With this small introduction, now I hand over the session to Dr. Narendranath sir. Sir, you can take over.
Yeah, thank you, thank you. Is it my slides are visible?
Yes, sir, visible. Please, can you make it full screen,
Yeah,
sir?
yeah, I will make it.
Yeah.
Is it okay now?
Yeah, okay, sir.
So good morning to, good afternoon to all.
Good afternoon.
Sorry for the delay, because of one of our camera in digital library is disturbed a lot. Just now it is getting ready, but now I switch over to my computer mode. And today's afternoon talk, what I'm going to give is hot rolling and characterization of shape memory alloys. And why hot rolling? So normally these shape memory alloys, if it is titanium nickel based, when we are going to make or give any new shape, for example, if I want to make it a rod or a plate, so there cold rolling is not a solution. So cold rolling, it will it will crack automatically. The when you roll it, it will crack. So the moment it cracks, so very well, it is not possible to use it. So that's why people are going for hot rolling. And whatever little work we carried out in this hot rolling, that is I'm going to present in front of you, all delegates. And the moment when we are talking of any alloy designing, so we have to characterize those alloy in different ways and means. And because we are talking of shape memory, so how to characterize and what are the techniques one can use. And if I am not characterizing this, if I say it is a shape memory alloy, people may not accept that. So for that, you have to go through this procedure. So with this little introduction, I will move on to my talk. And this is what introduction, rolling. So normally this everybody knows because basically we're all teachers, and manufacturing process is a primary process when we are talking. So there are two routes are existing, and now there are so many other routes came, but at large, so it is not still more popularized, and liquid metal route is one, and that's where almost more than 90% of the product what we are going to see today, it is through that route. And another one is powder metallurgical route, and both they have their own advantages and disadvantages. And when we talk of liquid metal route, we can get very high density, so closer to our theoretical density we can achieve. So the moment when powder metallurgy route you are going to choose, so if it is a cold impact, if we are doing cold impacting, so normally porosity is there. So this porosity you cannot totally eliminate. Or if you go for hot isostatic pressing, you can achieve near net shape product with very high density. When we are using primary process, normally, so that is not the end. Suppose any casting product, if you are going to cast it, you cannot straight away use that. So then we have to go for some of the secondary process. Depends on the need, and depends on the product. So here, so people are using wire drawing, they're using equal angle channel process, they're using, and there are so many other processes, like for example joining process. Okay, and rolling is also one such process. So in this process, rolling you can do either at room temperature, or I can do it at room temperature, so or closer to recrystallization temperature. It is not above, it is a little less. So here, when you are doing at room temperature without any heat in it, so not much metallurgical changes you can notice. When you are going for any process with temperature, and you can see the changes is happening with respect to crystal growth, or even further metallurgical changes. So when we say art, so normally it is above recrystallization temperature. It is greater than recrystallization temperature of that alloy. Okay, so that is the meaning of that. So if I am using anything lesser than that, still I can call it as cold only. Okay, so with this let us move on. And introduction to our shape memory alloys. So those who already worked in this and working in this, and thinking of to work. So these are all the few very important properties. So here this is one of the alloy. So when I said one of the alloy, I am referring all the time titanium nickel or nitinol. So this is the alloy where you can you can strain up to 8%. You can stretch it. If this is the length of the wire, you can stretch it further up to 8%, and when you leave it back, it will come back to its original position without any change in dimension or change in shape. So that means recoverable strain. It will recover back to its position. So that is one of the most advantages of this shape memory alloys, whether it is copper based or nickel based. So because when we are talking of titanium nickel, so when those who are looking at as a biomaterial, so for them it is one advantage is it is having very good compatibility. Biocompatibility. So that means when you are replacing any hard tissue in your human body, so for example any kind of screw you want to put as hard tissue, so this, when you are placing it inside the body, it is it is having very good compatibility. It will allow things to heal quicker, and it won't affect the human any kind of digestive system, or any normal human being, whatever he does, he can do. And cell growth is very good with this material. If it is not supporting cell growth is not supporting, then it is very difficult. So that means there is a clear cut demarcation you can notice. So because when we are using titanium nickel as a good biocompatibility material, naturally it's having very good corrosion resistance. So it won't corrode so easily. So it's having very longer life, and whatever as per the medical studies, what they says, even whatever the ion releasement is there in that your in your body, that is well within the limit. If it is crosses its limit, so it affects human health. The moment it affects human health means it may attack any of the human organ, and it will start malfunctioning. So that is not happening. Other one is, so next is excellent mechanical properties. So excellent mechanical properties is in terms of anything you take, whether it is a for any kind of higher loads you want to apply, any kind of dampers you want to use this, so it will absorb very good energy, and very good wear resistance is there. All these whatever you can list out mechanical properties, it is fit into that. So it shows all the data better than any other alloy among the family. Okay. So next is phase transformation. So phase transformation temperature can be varied according to the requirement. So that means phase transformation temperature is nothing but, so suppose you are going to use it as a biomaterial. So naturally biomaterial means human body temperature, human body temperature, whatever it is there. For that it should you should tailor the material. Suppose if I am going to use it in subambient, where I want to use this at minus 120 degrees centigrade. So if that is the case, I can tailor this material. Where the transformation is taking place between with these temperatures. Okay. Suppose if I want to use this in say higher temperature, plus 120 degrees centigrade, or even more. Yeah, I can use. Only thing is, I have to think of whether can I use binary alloy. Binary is nothing but only titanium and nickel. Or else, if I want to go for further lowering the temperature, transformation temperature, or further rising the transformation temperature, I have to think of ternary alloying elements. These alloying elements is available. Okay, if you see the literature, if you want to go for, say, suppose 600, 500, 550 temperature, so there are elements where I can use it as a tracing elements. Then I can raise the transformation temperature to that level. That means only at that transformation temperature this starts working. So here any lowering is also possible. So this is very beautifully you can vary for from very long range. That is one advantage of this material. Similarly, among intermetallics, near equiatomic is having very good properties. Near equiatomic is nothing but say 50-50. Then only it is near atomic. So anything variation is plus or minus 1%, plus or minus 1 atomic percentage. So then only it is called it as near equiatomic. Suppose if it is 75 is nickel and 25 is titanium, then it is not near equiatomic. So it is nickel rich. Suppose titanium is 75, nickel is 25, then it is titanium rich. Okay. So then you may not call it as a shape memory alloy. Then you have to call it as a simply alloy, because it may not have any kind of shape memory effect in it. So when you have this kind of near equiatomic alloy, it is having very good ductility in it, where you can for machining purpose one can think of. Otherwise, whatever you designed, if it is not possible to machine it, if it is brittle in nature, so the application will be limited. So when the ductility is there, so people will find more applications because machinability is very easy. So this is actually difficult to cut material. Even though difficult to cut material, with your non-conventional machinings, people are working, like what we are also working this material in on difficult to cut machining material in our laboratory with wire electrode discharge machining. So we gave very good, we got very good results. So very good impact resistance is there. And because of these things, because of all these advantages, the number of industrial applications is more. So like actuators, valves, etc. If these properties, if these good characteristics is not there, then the number of applications, industrial applications will reduce or restrict. So with this, we will keep on moving. Little bit history of shape memory alloys. Is it so? Any topic, anything you want to, you want to do in research, or you want to learn more of any one of the topic. So you should refer back history. What exactly the history and when it started, how it started, and what exactly the history says. So here, the first reported in the material is, AUCD alloy in 1951. So they found shape memory effect 1951. But at that time, not much usage. So just they identified. Then again, they noticed in this alloy with 1953, and later on actual applications were realized. So after 10 years of gap, the 10 years, it is not that there is no work is carried out. There is a lot of work is carried out in front, in research front. So they may arrived with so many doubts, whatever it was existing, they may cleared. Then actual applications were realized. Then they started using this. So this is actually 1963. They found in titanium nickel. So then copper based is coming into picture after a gap of 2 to 3 years. So then they found, okay, copper, aluminum, and nickel. When they used, they revealed, there is an SME here. So then this is also a copper based shape memory alloys. So then after that, there was a lot of research, but actual research on titanium nickel, particularly titanium nickel. So the Miyazaki is one researcher from Japan. He did a lot of work on this, and like crystallographical study and how transformation is taking place and what kind of mechanism is involving. He thrown almost, he cleared almost all the doubts, pertain to that. So later on, people are started working in different aspects, different fronts, and they found, different applications, and they started adding ternary elements. Then the application bandwidth is start increasing more and more. So this is what a little brief history of shape memory alloys of this nickel, titanium based alloys, and applications you can see here. So when you see applications, so this teeth you can see, over the teeth they put some kind of clamp, and between the teeth you can see there is a wire, and these things they stitch it together, and at the end here, so they are going to tighten it. So when you are going to tighten it, that, so if normal wire, if it is there, it will break. So when it breaks, you cannot use. So whereas here, because of 8% strain recovery is there, so when slowly, when the teeth is coming, when the teeth is like this, when slowly it is coming and become straight, so the wire length is going to reduce. So how to tighten that? So they are going to do that mechanism. That is possible only because of 8% strain. So if this is not there, they cannot use it this. And because, see, when they put it in the mouth, so all kind of foods they can eat, all kind of drinks they can take. So now here they have to ensure that whatever nickel titanium is there, they have to ensure that when I am taking everyday day-to-day life, it should not affect our body system. So that is medical side, medical front, they gave reasons. Nickel is highly poisonous actually. Among top poisonous elements, if you take in the periodic table, this stands in third. That means just simply if you take a powder, in the powder form, and even if you smell it, or if you while taking food, if it goes as a tracing element in your body, so that you may become totally unhealthy. So that's why titanium, when it is there, the titanium is taking care of nickel ion releasement. The titanium creates a rutile layer, RUCTILE, rutile layer. So this is very hard oxide layer. So nickel is not nickel ion, whatever it is, it is releasing. It is very difficult to break that and coming out. So these are all the advantages of other side. And you say another previous slide shows as a biomaterial. Here you can see this is actually these these things. Actually, it is a kind of small portion of wing. It swings. It swings. So you can lower it. You can. How I can give example is like like our bird's wing. It will bend. So how to make this to bend? So here they are using actuators. Okay, earlier. Now earlier they used to use hydraulic mechanism. Suppose if you press the button, there is an hydraulic mechanism where it will pull the wing to required position. Now they replace that with simple actuators. These actuators is connected through your titanium nickel shape memory wire, and through heating or cooling, so it will pull it and it will goes back. So that way people are using. So this is you can just think of replacing hydraulic system with this, how much weight reduction is taking place. And other simple examples I am giving. So this is one safety switch. Okay, so you can, this is actually the whatever I rounded off, this is actually titanium nickel wire. So when I said transformation temperature, suppose this switch, it will sense the temperature. If you designed say at 40 degrees centigrade, it will sense it, then it will discharge once it crosses 40. So a kind of opening closing of gas. Okay, so this is the last I said now, these are all the dental accessories what they're using to a human body for their purpose. Similarly, electrical micro switches, and this is actually one kind of mixing valve where there is a one SMA spring and this is one bias spring. Actually, this SMA spring is act as a teacher. It acts as a teacher. So this is controlled by the mixed water. What is the temperature of water you are going to fix it? Correspondingly, this SMA spring will act. So when it compresses, so this moment, the cold water and hot water, see here, the inflow of cold, the inflow of hot, that depends upon how this SMA spring is actuates here. So that means that depends upon what is the transformation temperature of this spring you designed to take care of this hotness. So if suppose if your hot water, if you say it is 40 to 50 degree, then it should actuate between that. For mixing is there and it's coming out. So these are all few applications. This is thermic safety valves. This is micro actuators, and heat sensitive elements. And this is very interesting. You can see this portion. This is actually a super elastic guide wire. So it's a human brain. So they're using this to remove some clots here somewhere. And just to think of if the straight wire, how this is actually two-way shape memory effect. Okay, they trained this wire in such a way that all the time it is going to become straight. Okay, it is going to become straight. So the tip, whenever it bends and goes, so how it is going to become straight again? Because it senses the body heat. So it senses the body heat. So that means whatever the heat is there here in your brain. So based on that, transformation is taking place. It is not, see, suppose this bend. It is not going to become that shape all the time. It is all the time going to become straight, and in that way it is pushing. So otherwise, if you become permanently in this shape, when you push further, then it should go like this, and it creates a kind of channel. So then there is no brain at all. So this kind of beauty you can see here. And this is another picture of SMA wires, how they're using wires, SMA wires. These are all the SMA wires. Okay, so to swing this, how they're going to use these SMA wires. So this is through heat. This I can do it through pressure or heat. So normally in these cases they're going to use a small amount of heat to bend it. And this is actually, this whole mechanism is happening with this simple figure. So what is this actually mechanism? This is actually the BCC. Okay, BCC. So body sintered cubic, when the material is in austenite shape. So now see here, I am going to cool it. So this is actually heat, through heating and cooling. When I am going to cool it, see here, it is going to become a next phase, that is called martensite. But when it is coming to this step, we call it as twinned martensite. So through twinning mechanism, it is going to change the order from BCC to monoclinic. So without changing any of its dimension. So it will deform. You are cooling it. It will, via twinned mechanism, it will deform it. It comes to deformed martensite. That's what monocyclic. Then once the thing is over, it is back to austenite. This is what two-way. Suppose in your human body, it's only one way. It won't go back. So whereas in industrial applications, it is going back. So now if I want to go back, so I have to heat it. So when I am going to heat it, so it will take the path and it become a austenite with again BCC. And this cycle keep on doing. So this is what people are doing. So here another one is this is what how start, martensite start, martensite finish, and austenite start, austenite finish is going to take. So that means when I am meeting, suppose if austenite starts, or say martensite start, heating, austenite starts and austenite finish. When I am cooling like this, martensite starts, that austenite finish to martensite start. So then martensite finish. So again reverse. So this way people are finding out. Again it is temperature dependent. So that temperature dependent is nothing but, so again it depends how what applications actually you are going to look into it. It all depends on your applications. So these applications is if it is human body, transformation temperature is different. If it is high-end temperature, transformation is different. Okay, so that you should decide at what temperature I should use these transformation temperatures. This will come through your expertise when you keep on working. So here, so there are some few typical properties you can see. So with copper based and nickel, so this is what titanium nickel, you can see the density is very good, and hysteresis you can see, hysteresis is nothing but this, suppose start to end. So this much hysteresis is there. So you can design, suppose I want a very quick return mechanism. So my hysteresis is only this much. Okay, say it starts at 5 degree, it ends at 7 degree. Suppose I want longer hysteresis. Okay, I starts at 10 degree and ends at say 30 degree. So this much work area is there. You can it's a kind of holding time. So any delay is there, you can go for longer hysteresis. In a quick mechanism, so suppose pick and place, it's very quick. So then you have to go for lower hysteresis. So that is one advantage. and compared to remaining. So similarly, you can see this grain size. So grain size you can go as low as up to 1 and as high as up to 100. Okay, that again depends on what processing routes you are going to use, and later on what kind of heat treatment process you are going to do, and later on what kind of secondary process you are going to use. So based on that also you can dictate, you can tailor made. And recovery you can see here, and transformation temperature you can see here. So this is only with binary. If I am adding copper here as a ternary, if I am adding zirconium here as a ternary, then these things, it may go further down, it may go further high. Okay, that depends. Now it is as a titanium nickel -100 to plus 200. That means around 400 degree variation is there, transformation temperature variation. If you adding copper or zirconium like this, there are so many. I gave only these two. So you can just further again widening the transformation temperature range. So it is left to, again depends on the application. And you can see here different systems of shape memory alloys, how these things is there. So when you compare to other alloying element, so titanium, nickel is you can get shape memory effect only near equiatomic. That's what 49 to 51. That is around 2% atomic variation. Okay, either titanium side or nickel side. So beyond that, you may get alloy, but it may not, shape memory alloy. And structural change. See here, that means mechanism. So there are two routes here. One is B2 is nothing but the BCC austenite to martensite. So whereas this one BCC via rhombohedral shape, one more phase, then it goes to martensite. It is like this. Suppose heating. So austenite starts, austenite finishes. Okay. So now this is actually B2 to M, or else I can add another curve. Okay. This is, now you see here, MS starts, MS finishes. So here in the bump area, you see there is no any other peak is there. Whereas if you see this B2R, is it slides are visible? No issue, no? Hello?
Yes, sir. Continue. Please continue.
Yeah. Thank you. So now, if you see this B2R to M, it is like this. Sorry. While heating, while cooling. See here, now there is another phase is coming here. So this is what? R phase, rhombohedral phase. So that means austenite to martensite transformation is taking place through rhombohedral, and people are using this as an advantage to shoot their applications. So that you can remove this you can remove through processing, through treatment, but you can increase also this phase. That depends again, how you are going to make it, for what purpose you are going to use it. So this is the way, and hysteresis is around 30, and structure is ordered. That means, so when you use this alloy as an application point of view anywhere, it won't fail at any lower temperatures. Even the structure is ordered, almost closer to higher temperature. Then only the failure will coming into picture. That is the meaning of ordered. And this is one diagram I am just showing because you people are know already, I think, maybe different binary phase diagrams. This is because when we talk of SMA, so why that equiatomic equiatomic is coming into picture. Equiatomic, okay. This equiatomic is here, you see. If you see this line, it is 50-50. It is 50-50. And the temperature is, say, around 600. So further down, up to room temperature, no change. All these things as projected as a straight line only. Straight line, no change. Changes is there only above 600 degree temperature. And because we are talking of SMA, so this is exactly near equiatomic is existing here. So that means only in this triangle area you can get titanium nickel. Only in this triangle area. If you go away from this, if you go away from this, so it is not possible. It is highly impossible. So you will get an alloy, but without shape memory effect. Without shape memory effect. So then you cannot call it as nickel, shape memory alloy. So that is the reason. So you have to, walk within this zone. Within this zone, if it is binary. If it is ternary, so suppose you are going to add Cu, Zr, zinc, whatever it is as a ternary elements. There are so many ternary elements. Now you cannot refer this binary. So further, for that you have to get a ternary phase diagrams are there. For that you have to see, like this it is there. So suppose if it is Ti, if it is nickel, if it is copper, then you have to find out what percentage of this, what percentage of this, what percentage of this. Then you have to find the point. Then you have to choose the required composition. So in this way, one can choose. So this is very important. And anything other than this, we are not interested. We are not interested. So there may be an applications for this rest of the diagram, but not as a shape memory alloy, as a simple alloy. Okay, as a shape memory alloy only here. Only this zone you can think. So such a close variation is there. That's why people are talking atomic percentage. Atomic percentage. So that means it is not weight percentage, atomic percentage. So after decimal, people are talking of this digit. So in weighing balance. So if it is weight percentage, we are talking of first one. So that much accuracy they are expecting. Otherwise, you will lose the shape memory effect. That's all. Nothing will happen. And this TTT diagram, temperature, time, and transformation temperature, diagram. Why it is so important here? I will just explain with a few, 1 or 2 minutes. See, temperature versus time, aging time versus aging temperature. So again, less than low temperatures they didn't record, because whatever the these things is there, these things. So lower temperature maybe same thing may exist. That may be the reason, because this diagram, each data represents numerous studies. So this is what our alloy, titanium nickel. When we are going to melt it and taking out, so we are not getting 100% titanium nickel. We are going to end up with either any one of these, any one. That means combination titanium nickel along with these phases, along with this. See, there are so many phases are there. Any of these phases may be there, and these phases, whatever these phases, other than titanium nickel you are seeing, these are all precipitates. These are all precipitates. And these precipitates, some are stable, some are unstable. Okay, and whether it is stable or unstable or combination of both, whether it is useful or not, that matters for us. Okay, along with titanium nickel, if it is there along with that matrix, if these things is there as in the form of precipitates, is it truly affects shape memory effect or not? So that is a question mark. So normally you cannot avoid these things. Definitely it will come, at what percentage you are getting these things, Ti3 Ni4, Ti2 Ni3, Ti2 Ni3, these things is matters. For that you have to use this temperature versus time during aging after melting. So then this is actually natural cooling. You see all these things are natural cooling. But natural cooling, suppose at this point is around say 680. I want this phase. So timing is 1 hour. So what I can do a rapid cooling. When I do rapid cooling, this phase, whatever it is existing, it is going to arrest and it is going to stay there. If we allow further, say it may take to reach to temperature, say 10 to 15 or 20 hours, then it transforms via like this. You will get all kind of phases. So this should not be. So for that, you have to thoroughly study literature and find out I need or not. So normally some are good, some are bad. It again depends on the applications. So this one has to take care. And example you take. Now example. Study the following behavior of rolled titanium nickel shape memory. So this is what quenching effect. So we talked of phase transformation behavior and superelasticity. So for that we subjected that to following treatment. One is at high temperature treatment, another one is at low temperature treatment. So this is, I said, no, to take care of precipitates. Whereas this is anyhow phase transformation behavior is a must. So because at what temperature it goes and what temperature it is cooling down. So that matters. Okay. And superelasticity. So when I'm going to stress subject to this, cyclic loading. So whether truly it is coming in this fashion or it goes and break or it goes and stays here. So this much residual stress is coming into picture. So these studies is a must. One has to see. We will see next slides. So these are all the parameters what one can think of if you are doing. So anyhow, you need vacuum controlled this one whenever you want to give, because you are going to use titanium. Titanium is very good friend of oxygen. So the moment when it reacts, titanium is talks with oxygen at high temperature, it becomes oxide, that is TiO2. So then you are losing the material. So to avoid, you should not allow O to interact with this during treatment. For that, you need some kind of vacuum controlled, or some kind of argon gas controlled. This kind of controlled atmosphere is there. And heating rate, one has to think, because when you are going to use your furnace, so very fast heating, say 15 degree centigrade per minute, 20 degrees centigrade per minute, it damages the matrix. So better go with lower heating rate. So that means uniform temperature distribution. At the same time, you are allowing more time to react with the neighboring element and make it uniform structure. Okay. So again, further holding time again, it depends. So 1 hour, 2 hour, 3 hour, that depends upon your transformation curve one can choose. And because if you want to have that phase, you can think of quenching or else natural cooling. Okay. So to study these things, we have to have, first we have to think of as received. So simply what we melted or what we purchased. Suppose later we have to give some kind of solid solution treatment. So solid solution treatment is ensuring that this is what high temperature treatment, so that the distribution of the particles, distribution of the titanium nickel or any unstable precipitates or any Ti rich sites or Ni rich sites, you are allowing that to become normalized and mix with the matrix. and aging, low temperature aging is 350, 450 and 550. This is just to allow precipitates to stable sometime, and this is what we used the facility. So this is what tungsten inert gas melting equipment. So it is available in our lab. Just a minute. Okay, I'll go back. So this is actually this one we can remove it. If you open it, this I didn't put that figure. I am sorry. So this is a window, glass window. You can open and see. And here there is a inside. Here this here. Inside copper plate is there, and 4 buttons are there. 4 pits, I can say 4 pits, and you have to fill each pit with titanium plus nickel ingots, titanium Ni ingots. Say for example, we used to take normally 12 to 15 gram. 12 to 15 gram. We are going to fill it here. We are going to fill it here. That is equiatomic. Okay. Then we are going to close the chamber. Close the chamber. Then see here. These locking mechanism is there. We will tighten it. We will tighten it. So then this is vacuum. This is vacuum. We will switch on the vacuum. So this is vacuum pump. So this vacuum pump. This vacuum pump, will suck all the whatever the external gas is there here in the chamber. It will suck. So now entire chamber is airtight. So nothing is going inside. So now once you are doing like this hour together, then we are allowing, this is argon gas. Argon gas of 99% purity. So through that we are allowing, we are filling the argon gas here. Then again we are creating vacuum. Then again we are filling argon. Then again we are taking out. So in that way 2-3 times we are making to ensure that there is no atmospheric air inside. Later, this is the gun. This is the gun. This is the holder. This is the holder. So because it is vacuum, during under vacuum it won't move. So that's why we will allow a small amount of argon gas to make this is to free movement. So then this is a a controller. We will switch. We will start this, and we will test the this pit inside material. So arc is establishing. Like this arc is establishing. This is the material. Arc is establishing. So then we are in, once arc is established, if you bring closer, starting will take place. So then you cannot melt. Then you have to open this. Then sometimes this is a titanium rod. So this is tungsten rod. This is tungsten electrode. So sometimes this arc, if this tip comes and they have established contact, it becomes like our welding. It is sticking. Then you have to open it. Then you have to take out. Then that day is gone. So again you have to redo. So this way we are melting 4 to 5 times. 4 to 5 times. Then like this one button is there inside this. What we will do? We will turn this. We will turn up down. We will turn it. Then again we are remelting. So 3-4 times to ensure that perfect mixing is taking place. So later this kind of titanium nickel button is forming. If this button, if it is good, see, shiny face. If it is reacted with oxygen, if it is not properly flushing out atmospheric air, and if you are not properly created vacuum, so this become dull. So dull in the sense looks like ash color. Okay. So the moment when it looks like ash color, so no need to think of. So you have to throw. Otherwise, if you take out ash, you are grinding it, you are doing all these kind of adjustment. What will happen? The composition is no more TiNi. So because more titanium you are going to lose if it is the ash kind of color. Suppose if it is a copper kind color, sometimes copper color, so nitrates will form. Nitrates will form. So whether this or this, if it is there, you have to reject. If it is shiny face, then you have to accept this. So this is the button just to initial stage to start your research. Later, see, this kind of furnace is required for rolling, hot rolling. This is actually side by side, so hardly 2 feet difference. I should take actually same picture. This is here only, so this is 2 to 3 feet. So this is the chamber. We have to open it. We have to open it. We have to place it. Once it reaches 850, we are putting here. This is the roller, and only one pass. After one pass, it is going that side. We will take it, and again we will place it back here. So the moment you are taking the button out, only you can do one pass, because by that time already temperature will drop down. Suppose if it is 850 at high temperature, it coming back, because these rollers act as a two rollers act as a cold sunk. So it is cold. So this is very hot, and the mass is very small. It will suck. All rollers will suck the heat. So it goes. It is coming 500 or 600 in that range, the temperature down. So further, if you are placing once again, the button become crack like this, crack. So that's why you put it back again, raise the temperature, wait for a while. When it reaches 850, so then you take it, do it like this. So this way for rolling, this is what hot rolling we did. So this I just simply wrote one figure to better understanding how rollers is there, how it is coming like this, it is coming like this, and how see 900-degree temperature is there, and the time taken. This is our rolling time. This is our rolling, because the rolling speed is 8 meters per second. Cycle time is 20 seconds only. Rolling time is 3 to 4 seconds. So now, so this is what by this time it should go back to furnace. Actually, as quick as possible. So it is going like this. So in this only before dropping down further, rolling should happen. If you roll somewhere here, so you can see crack on the button. Okay, so this is what the rolling procedure. And solid solution treatment, what we are going to do is the slow heating, soaking temperature. So here, what is the heating? You should tell. This is first soaking time to remove any kind of things is there. Then this is second soaking time. So then afterwards, so see time. I didn't put any time. You can take any amount of time. It is left to you. So temperature. So general curve I shown here. So this is just this first soaking and second soaking. This is the first soaking is just say some 20 minutes, 30 minutes to get uniformity, the temperature distribution. So then further heating, so that it is, if you go straight away like this without this, you can go, but thermal gradient, because of thermal gradient, cracks may come. So to avoid that, the people are giving a small amount of first soaking time. And after rolling, so this is what looks like this. You see, I said no, this shade, this colors and all. So this is actually nitrites. So this is dull is kind of PaO2, something like this. So because rolling we cannot avoid. So in melting means it is very tough. We have to reject, because rolling is already melted. So whatever the amount we are going to lose, Ti or nickel. So it is well within the limit. We checked. After taking the scale, after taking out the scale, so this is what the material looks like. And then again, this we did it in SCM VDAX. So then we see the compositional analysis. So it shows it's fine. Okay. So then further things. And this is one more treatment. So a small rod. So see a small rod. Suppose I don't want to become like this. If I want to avoid these things. So if I want to avoid these things, so what I can do, I can go for this if you have facility. So this is what a quartz tube. This is quartz plug. This is titanium nickel. So here you place it inside. This is actually rod I placed it. So if you want, you can put it plate also. If you have big quartz tube, then you place it here. So this before placing, you have to get a vacuum here inside. So this tube chamber inside tube area, you are going to connect to vacuum pump and you are going to suck out all the atmospheric air. Then you are going to place it this. So after that, you are going to, after placing this, you are going to seize this, the kind of welding, glass welding they are making. So then it become a one tube. Both ends are closed. So here inside there is a nickel, titanium nickel rod. Okay. So this you can put it in furnace. To get it, clarity in it. Okay. This is what people are doing if you have facility. Whereas in our case, this furnace we used, this is the heating chamber. Here inside, we used to put a boat. Inside that we are going to put it sample, and this is argon, and here we are going to flush it, and here you are going to see it, and here flow rate we are measuring. You can see here there is a beaker here. So bubbles per minute. So we are going to set it. So we will see. So any bubble, suppose say 80 bubbles per minute we are setting, the flow rate is constant. Suppose if later after 1 hour bubbles rate is come down, so leakage may be there here and there leakage. Okay. So then we are increasing the flow rate. So to maintain that bubbles. So this is what furnace we used, and for all high temperature and low temperature treatments. And this is what the equipment we used for further studies. This I think everybody knows. So this is, you see, after after seizing, after closing, then putting inside the furnace. After treatment, we taken out. Now we are breaking this. We have to break this. The quartz tube is going to break. You will get a fine, titanium nickel rod. And this is what the rod we used. So these things is for metallurgical, sample preparation for SCM to study microstructures. And this is what the XRD, everybody knows this XRD mission. And this is differential scanning calorimetry. And this is what the diamond cutter. So this is what the material. So we used to take out 20 milligram flat sample, 20 milligram for DSC. So a small flat, low speed cutting. This is low speed. You should cut low speed. If it is high speed, because of the temperature, here itself transformation will take place material. Very much low speed, and you have to monitor very carefully, and you have to take 20 mg specimen, and you have to collect few number, say 5, 10 like that. Then you have to weigh which is closer to 20, and then which is flat. That one you can choose for DSC studies. That gives nice result. And this is what scanning electron microscopy. So this is what the instron what we used for. This is actually not dynamic study. And this is simple grippers we used. And if you want more accurate, you can put here strain gauges here. if you want more, so strain gauge setup is available. That itself is very costly. So that means now when you are going to measure here, what is the guarantee that there is no slippage in the grips? If any slippage is there in the grips, so naturally it affects. That means your strain, whatever you are showing, percentage of strain, it includes your grip also, your slippage also. So you have to ensure that. That is one error, people are doing. So characterization, whatever earlier I shown that figures, same thing I wrote here: optical scanning, differential scanning, micrometry, X-ray, and stress strain curves. Okay, and transmission electron microscope, atomic microscope. All these things you can use, but we use this only. We are discussing. And for example, SMA product, if you want to use it for MEMS, application, what should be the criteria? So that means it should have low residual stress, it should have high actuation speed, durable and reliable of shape memory effects, wide range of choice of working temperature, good resistance to surface to wear and corrosion. So when you designed now SMA, so for this application, it should have the following characteristics. So if it is not meeting any one of these, so then you cannot use. The life will come down. So, or suppose say high actuation speed. So per minute, how many actuations you are expecting, or per hour, how many actuations you are expecting. So these things is coming into picture. Okay. And see XRD, when you go for XRD, so you should know what exactly the angle range you want to scan. Okay, I said 20 to 30. So suppose you may require 20 to 50 itself. It depends on the underlying elements and scanning speed. So better go, if you go very high scanning speed, it may not detect properly peaks and all. So better take 3 to 4 degrees per minute, so that it gives very good result. And depend upon the underlying, you may choose target, what kind of target is required. There are 2-3 targets. So this is copper target we used. So based on that, we tested the tests. Okay, you can see intensity, there is no unit, and as received material, as received titanium nickel, so whatever we received, and 2 theta versus peaks you can see. So now you can see here B2 is there and B19 dash is there, and apart from that, these precipitates is there. So that means BCC B is there, and monoclinic B19 dash is there. Okay, and apart from that, precipitates is there. So this ensures, okay, this ensures. But because this is high peak, so this is high in as received, the most of the matrix is austenite. Most of the matrix is austenite. Okay, and suppose I heat treated that. When I heat treated that, solid solution degree temperature at 800 to 850 degrees centigrade. So now you see, is it any changes is there? Okay, is it any changes is there? So the reduction of intensity was reduced here. The B2 reduction was reduced, and peak broadening is taking place. Okay, and there are other prominent peaks is coming. So that means high intensity peak in previous case like this. Now the like this. Just a minute. Broadening as well as the height is also reduced. See here. So previous case as received is this, and after treatment is this. So when you are discussing your result, you should talk in terms of height and broadening and other peaks importance and its intensity. When compared to previous one, now this B19 is increased here. So that means along with austenite, so partly martensite is there already in the structure, and other precipitates is there. So this is one has to check through only your peaks. And if you do same thing after 800, 350, 450 and 550, so low temperature retreatment. So in this case, how B2 is there, B19 is there, and remaining precipitates is coming into picture. And this if you want to do quantitative analysis in terms of percentage, so with the normal XRD is not possible. Then you have to go for high-end XRD, So then automatically they will tell. So what is the percentage of this? What is the percentage of this? Whether it is increases, whether it is decreases with respect to your previous graphs, it talks. So now you see, this is what we did. So with high-end X-ray, see here. So it gives like this pie chart. So titanium nickel is around 77.8, and nickel titanium is 4%, and nickel titanium is 5.1%, and nickel titanium is 13%. Now you can think everything is nickel titanium. Everything is nickel titanium. Then what is special in it? So that means now you should correlate this with your previous XRD. This is B2. This is B2, high intensity peak, and this is your B19. These things precipitates. This way you should correlate. So because the peak like this refers this refers this. So otherwise everything looks like nickel titanium. So it won't tell which phase, but you have to refer back and see the intensity of the peaks and talk. Okay. And DSC. So when you want to go for DSC, differential scanning calorimetry, so people are asking what is the heating and cooling range. Okay. So because normally DSC was room temperature to higher temperature they are doing, say suppose 30 degrees centigrade to say 200 degree. So it is not an issue at all. When you want to go for negative subambient temperature, then problem comes. Subambient temperature, because the chamber, the heating chamber and cooling chamber, you have to start with -50 first. From there it should go to 150. Then from there it is coming back to -50. Now -50 to room temperature, you have to use liquid nitrogen. You have to purge it. Then you should know how to slowly rise the temperature. Then again room temperature. From room temperature to on top, liquid nitrogen is not required, but argon atmosphere is required. Okay. Whereas here liquid nitrogen as well as argon atmosphere, because whole process is under a controlled atmosphere. So whereas here, so again liquid nitrogen, so you have to purge it. You have to flush it. So that is again, it is a the people are not every day they are not using this, because the setup has to change and it requires a long time. Okay. So if there is room temperature and above, they are very happy to do it. They can do it like X-ray and XRD and SCM. Very quick they will do. So, but cases is like this. In our case, it is subambient. So then you should tell the range, at what range you are thinking. So if you say -150, it takes more longer time to reach -150. From there again to room temperature, then again going up. See, that's why you should specifically tell to save the time. And heating and cooling rate, now normally again here also you should go as low as possible. So 3 to 2 degree, 3 degree, so 4, 5. So if you go more than this, it will quickly heat where you cannot sense the transformation in a proper way. And atmosphere, what atmosphere you required. And see, when you did the tests, you can see these kind of peaks while eating. While eating, you see here, it started from here, okay, na? So minus 50. So eating, see here. So at subambient itself, transformation is taking place. Austenite start, austenite finishes. So that means lower than the room temperature, these things is existing. Then after eating, it goes up to 100, I think 150. So then cooling is taking place. So see here, when it is cooling, so after room temperature, you are using liquid nitrogen, it is coming back. There is no major peak here. No major peak. When there is no major peak, so you can think no major peak, you can think. So it is very, not in a prominent phase, martensite. So then you will think, okay, it is not, whatever the alloy you designed, it is not showing any martensite phase. So that is only austenite is there. So people may not accept. So then when you see solid solution treated, see here, solid solution treated, nicely you can see here a beautiful prominent peaks you can see here. So martensite start, martensite finish, martensite peak, okay, and this is what hysteresis of martensite, austenite, hysteresis of martensite, okay, hysteresis of martensite. If you take overall hysteresis from year to year, that means 30. If you say it is 30, so if you say this is minus 20, overall hysteresis is minus 20 to 30. That means both the phases will start and finish. Austenite start and finish, and martensite start and finish. So this is the hysteresis. Suppose if you want to bring it closer, I want to end up with minus 10. I don't want to go for plus 20. So then you have to think how to tailoring this. This is actually lowering the hysteresis. How to tailoring, that one should think. And again, aged, your low temperature aged you can see. And what I said, rhombohedral phase you can see here. Rhombohedral phase. Now it is eating. When it is eating, austenite starts, reaches rhombohedral, research, austenite finish. Whereas here there is no R. So in some cases, in both the cases, cooling and heating R may appear. So this is all, it depends what is the processing history and what is the cooling history. What is the treatment history, heat treatment history. And SCM results. So here, very clear, no need to explain. So you have to have some kind of agent. So for us, this is the agent, okay? It is not general. So, and what you want to see, that one should know. When you are going for XRD, scanning electron microscopy, you should have a sketch of for different magnification. And suppose if you want to have any kind of line scan, so that I can talk about grain center. So line scan means this is the one grain, this is one grain. If this is the boundary, you have to mark it here. You should draw a line. So now from this center to this center grain, across the boundary, what is the composition? If it is nickel, if it is titanium, how it varies? Is it goes high and then coming to level like this? The nature, it depends on what percentage it is there. Accordingly, it will show. And redox analysis. And this is actually very typical. Titanium nickel is very typical. So whatever these things you are seeing, these things actually, these are all not holes. These are all precipitates. It is actually it is like this. So precipitates is like this. Precipitates is like this. Because of polishing, this will go, and it looks like this, like a porosity, but it is not the case. So this is because of our poor, polishing and etching. So wherever you are seeing that, that is not the case. And this is solid solution treated. So here also, if you see like this, you can see grains. But unfortunately, we tried because we are using HF. Any small amount of HF is very dangerous, but suddenly it will burn the surface. We tried for different microsecond to 30-40 up to 30-40 second. We miserably failed, but optical thing, it is coming very nicely. And same thing you see aged. See here, this is actually optical. Whatever optical we are seeing here, same structures we seen under SEM, it is showing in that way. This is actually different level of rolling, 20% to 30, 40, 20, 30, 50, 60, and 80, and 90%. You can see here from A to F how the structure is fine-tuned. So how the structure is transforming with rolling. Okay, and each structure is having its own unique beauty in it, and transformation temperature in it. Each one is having its own transformation. So that means for different applications, I can use for 20% for that transformation temperature. For this transformation temperature, I can use for 30%. So nicely, you can see how much structure is changes. And this is again hot roll structures. We tried with different, but again, if you zoom these things, again it looks like our previous sketches, empty, pits. You are seeing pits, but actually it is decorated with precipitates. And this is what E-mapping, elemental mapping. So this area, this is the area we mapped. So here you see, if bright is Ti, if dark is Ni, if you match these two, if you put one over other, it is coming this figure. So that means either dark or light is equal. So dark or right here, dark or light is equal. So that means nickel and titanium is equal. It is there. So we checked that with for big area. We checked at a triple point. This is what triple point is. Nothing but this is one grain. This is a grain 1, grain 2, grain 3. In this area we checked. So there also it shows not much difference. So that means whatever 50-50 is there, it is there. And line scan, I told how we draw line scan. So this is the area we draw line scan. So there also nicely it is this refers red refers titanium, this refers nickel. So that means throughout the structure both are equal. And this is we checked at this point. We checked what is the element present here. You see here, atomic percentage 48.47, 51.53. You remember our phase diagram, triangle point coming like this 50. So that is well within that. Okay. So by proving all these things, it is equi-atomic titanium nickel with having very good transformation, shape memory effect. And superelasticity we checked. Superelasticity, dynamic testing parameters, and that's what we said. The cross-head speed is 0.3 mm per minute, and at room temperature, because we don't have facility to having heating chamber. So this is what, when we pull the wire, when the pull the spring and return it back, so there is no deformation. You see, when you are leaving it back, no deformation. Initially it will come back to original position. Like this, if you do n number of times and return it back, so you should come back to original position. Suppose with the time, if it stops here only, with the time, if this is increases more, then that much residual stress is there. Then it is not usable. Say if you said this spring is 10,000 cycles, so up to 10,000 cycles, it should not show any residual stress. If it shows, means we have to replace or something is wrong. So that means this with load. So this is what loading and unloading is taking place. Loading and unloading, first cycle, second cycle, third cycle, fourth cycle, like this. And here, actually, during unloading, we don't have a proper mechanism to measure it. So while loading, it is going nicely. When it is unloading, at some point of time, it records value. After that, it won't record. So then, forcibly, it is bringing back here. Then we are treating this as residual stress. But if you use high-end instant or any high-end tensile machines with dynamic characteristics, so it is coming like this. Going. So this is what plateau. It is coming back here. So that means exactly origin. So no residual stress. If it is with the time, it is coming like this, then this is the residual stress is accumulated. Okay. So that you need high-end in the sense sophisticated measuring devices. So this is heat treated. So see here, this is the temperatures. In previous cases, no flat use. Here you see, this is what the flat use. This is what the flat use. So now this much what we are talking, a strain, actually it should not come like this. It should come like this. Okay, because in one cycle, if this is the amount of residual stress, nobody will accept that. Okay, this is, I said, the limitation of the equipment. And these are all you see here. Up to a year, recording is taking place. After that, sudden it is coming to origin. So if you see this, there is no residual stress as per this graph. But actually, there is a residual stress. It should come and stop somewhere here. So it never ever goes like this fashion. So in shape memory alloys. Okay. One transmission electron microscopy studies we did. For this, you have to have very thin 3 mm sample. Thickness is a micron, and you have to polish, and centrally you should get a small hole. Then ion ball milling they will do. Then if you cannot hold by hand, if you hold it forceps, and if you see other side, the light should transfer. Light should transmit. So then they will place it in TEM. So there, whatever precipitates we are talking, these precipitates they are studying. Precipitates. See, these are all the precipitates. This is with TT. These precipitates, its length, its orientation, all those things people are doing. So how much it is there, how much percentage it is there. So now that you can see here. So when we study, this is actually ABC parameters. On this slide, I don't have knowledge. This is actually we tried, but I stopped. So ABC parameters. So in your BCC structure, BC structure, how lattice parameters are there. So those things we can study here, but we didn't do this. We stopped. Okay. So, but with this, you can see here a nicely titanium nickel is there, and with this we can prove on that. See, micron is 0.1 micron. With this, we can prove that there is a beautiful precipitate is grown. So, some applications I am showing. So, this is Frangi bolts where people are using. See, this is the joint. This is the assembly. This is the assembly. Here you see here. So, designed to deploy stored components. So, compress actuator, assemble Frangi bolt joint, activate heater, fracture bolt. Ultimately, we are going to fracture the bolt by activating the heater. So, this is titanium nickel. So, you want to make it this and this separate at high altitude for some reason, So then you assemble it neatly. When you want to detach that this main part from this body, so for that time you have to program it in such a way that at that time it should heat, then it should simply detach. So through SMA, this is actually made up of SMA. And deployment of sonar panels, when it is along with that, when earlier it was along with this, when it reaches the altitude, so it is unfolding is taking place. That is also release of cover doors. This is also through SMA components. And with this, thank you. And this is our institute. And any questions is there, I am ready to receive. So
Hello, sir. Can I ask a question?
yeah, please.
You have used Frangi bolt.
Not me, example. It is,
What is that Frangi bolt? What is the meaning of this term?
we didn't use. People are using in industrial applications. Okay.
What is that? No, I'm just asking.
This is a suppose. See, this is main body. This is main body. Okay. So A is main body. B is an attachment. This attachment we want to detach after some time. So how to do it if it is at high altitude? So then these kind of bolts they are going to use it by heating. This will become, this is the things. While heating, it will little bit, expansion is taking place through shape memory effect. So by that time it will just detach. This is what I am saying.
Okay, sir. You are using one term, Shikimori effect. What is that, sir? Shikimori effect, some term you are using.
Shikimori?
Couldn't understand. Yes.
I didn't use that. Can you repeat? Can you tell neatly what it is?
Just you have said the effects.
Shape memory effect.
What is that?
Shape memory effect is nothing but, see, when the alloy you are going to, when you are going to, load it, at certain point you are going to unload. Okay. In normal wire, it won't return back. Is it returned back? Normal binding wire, is it coming back? It won't come back. Whereas shape memory alloys, it will come back to its original position. So this is what shape memory effect.
Okay, thank you.
So
Sir.
this is.
Can I clarify, Mr. Pankaj Kumar Singh, sir?
Yes, sir.
See, what
please.
professor is referring is shape memory effect and shape memory super elasticity are the two unique properties what he is referring to. Shape memory effect in the sense that whenever you do some thermal cycling, suppose you have a wire, you wind it into a spring form, okay, at a lower temperature, and when you heat it, again it will go back to a straight wire. Means it is remembering its predefined shape. The predefined shape was a straight wire. By deformation, we have wound it. When you heat it, it is going back to its original shape, that is a straight wire. So that is called as shape memory effect. Whereas
Okay.
in case of super elasticity, what sir has written now, what we do is we stress at some point, we apply stress, and at some particular temperature, means we call it as a 30 degrees above AF temperature, that is austenitic finish temperature, at some particular temperature and at some particular stress, when you load and unload, it will come back to its original form. Means the kind of elasticity what it is showing is to the extent of 8%. That's why we call it as super elasticity. These are the two interchangeable terms usually we refer. One is for thermal cycling, one is for stress cycling. If I am right, Professor.
No, you are right. You also worked in same area.
Yeah.
Yeah. So Professor Raju is also
No, I
expert in
just
this.
took an opportunity because he was having his coffee. I didn't want to strain him. So I just answered it. Two unique properties. That's all. Am I
Okay.
clear,
Thank you,
sir?
sir. Thank you, sir. Thank you.
I will show one slide if it is there. I will show one slide whether it is working or not. Sorry, one video, small video. ಅಲ್ಲ ಅದೆಲ್ಲ ಹೋಯ್ತಲ್ಲ ಎಲ್ಲ ಹೋಯ್ತು ಲಾಸ್ಟ್ ತೆಗಿತೀವಿ ಹಲೋ ಹಲೋ
Yes, sir. You're audible, sir.
Yeah. So is it
Benny.
IIT Bangalore? ಕೆಳಗೆ ಆಮೇಲೆ ಅದರಲ್ಲಿ ಲಾಸ್ಟ್ ಸ್ಲೈಡ್ ಇಲ್ಲ ಬಂದಿಲ್ಲ ಓಕೆ ಆಗ ಬರೀ ತೋರಿಸು ನಿಮಗೆ ಅಷ್ಟೇ ತೋರಿಸು ಹಲೋ ಇಲ್ಲಿ ಮ್ಯೂಟ್ ಮಾಡಲ ಹಲೋ
Yeah, sir.
ಸೊ ಕೈಂಡ್ಲಿ disturbance is there? Hello?
Sir, have you played that video, sir?
ವಿಡಿಯೋ ಅದು ಏನೋ ಪ್ರಾಬ್ಲಮ್ ಇದೆ.
It's okay, sir. No problem.
Yeah.
So, any other participants, if you want to ask any questions, please.
ನಮ್ಮ ತಲೆನೇ ಕಾಣಲ್ಲ ಅದ್ರಾಗ. ಸಾಕು. So if anybody wants to visit our institute, so feel free to visit. You can mail to me so that I can help you in this regard.
If any queries are not there, shall we end the session? Yeah. Sir, I think no more questions, I think.
Yeah. So thank you, Professor Raju.
On this occasion, I wholeheartedly thank you for giving such a wonderful lecture, where you have clearly shown how the shape memory effect, your super elasticity, and even the number of cycles you have very clearly shown. It was very nice to see those kind of graphs, because it's only possible with nickel titanium, and wonderful graphs to see the super elastic effect. Thank you very much, sir, for your giving such a in-depth knowledge about the microstructure. We could clearly see how best you have done the research on nickel titanium alloys. You have clearly distinguished different phases what was existing in the material, and you have clearly shown people how to characterize it. Thank you very much, sir. At the outset, I take this opportunity.
Thank you for you and your institute.
On behalf of our institute, our department, we are very grateful to you for delivering such a wonderful lecture, sir.
Please, do visit here.
Sure, sir. Sure, sir.
Thank you, one and all.
Thank you, sir.
Thank you. Bye.
Bye. Dear participants, the feedback forum is shared. You can please use the Google link to give your feedback on the session. Thank you.